Today we're going to talk about rational zeros. Just want to point a couple things out. This is the variable p. This is the variable q. Here I have a ratio of p over q. And here I have a ratio of positive p over q and a ratio of negative p over q. There are 2 pages of notes to copy here just because I made the text really big. So go ahead and pause the video and copy this page. And then pause the video again to copy this page. All right, let's do some examples here. So the first thing we need to talk about is P and Q. So P is our constant term. So if you remember, your constant term is here at the end without a variable. So P is equal to 4. Q is our leading coefficient. So in this case, Q is equal to 1. Notice I don't worry about the sign at this point because all of our possible rational roots or our possible rational zeros are going to be positive and negative. So we're going to end up with a whole bunch of positives and negatives anyway. So we're just going to get our, just pull our numbers out. So when we're looking at this, we need to look at the factors of 1 and the factors of 4. Well, 1, pretty boring, 1 times 1. 4, I can have 1 times 4 or 2 times 2. So now I'm going to list all of my possible rational roots. Okay, so that's all of the possible combinations of P over Q. So in this case, it's super easy because my Q is 1. So I've got 1 over 1, 4 over 1, and 2 over 1. So I plugged in each of my P values and each of my Q values. Each of these is then plus or minus. And so I'm going to simplify, and all my possible rational roots when simplified are going to be plus or minus 1, plus or minus 4, plus or minus 2. And I'll often go ahead and rewrite them in increasing order. So plus or minus 1, plus or minus 2, plus or minus 4. All right, now I'm going to graph. So I plug the equation into the graphing calculator, and I have a couple equations in here right now. So I have to make sure that only the one that I want to look at right now is turned on, and then I'm going to graph. All right, so when I'm looking at this, I see that there are 3 zeros. And when I'm looking at these zeros, and let me backtrack, zeros would be places where the graph crosses the x-axis. I am only looking for rational zeros right now. So that's really important. And rational zeros is any number that can be expressed as a fraction p over q. So the only possibilities are the 6, I almost said 3, the 6 possibilities right here. So plus 1, plus 2, plus 4, minus 1, minus 2, minus 4. And I picked this one because I thought it was pretty easy to see. So when I'm looking at it, I have a number there that definitely, let me bring this closer to the camera. When I'm looking at this, I have a number here that definitely, trying to point, there we go, that definitely is not a 1, 2, or 4. I have a number here that looks like a 2, and I have a number here that is definitely not a 1, 2, or 4. So again, if it's not a 1, 2, or 4, either positive or negative, it is not a rational root. Now, I just want to confirm that these are in fact my zeros. So I'm going to hit I'm going to hit trace, not second trace. I'm going to hit trace, and then, oh goodness, silly me. Yes, second trace, there we go. So let me clear out of there and just show you again. So I'm going to hit second trace and then 0. And I'm going to go ahead and find the left bound and the right bound. So see where it says left bound right here? I press enter on the left hand side of where that intercept is, and then it asks me for the right bound, and so I'm going to press enter again, and then it says guess. Well, we don't actually have to guess, it'll do it for us, so we're just going to press enter again, and it shows us that that value is +2. So I'm going to put down the calculator, pick back up my pencil here. So I have been told that +2 is a rational root. So now I have to prove that with synthetic division. So I'm going to set up my synthetic division, put my 2 out here, copy in my coefficients. So 1, -6, 10, and -4. And now I'm going to go through my synthetic division. So I'm going to bring down my 1. 2 times 1 is 2. Add them together, that gives me -4. 2 times -4 is -8. That gives me 2. 2 times 2 is 4. Add them together, and I have a remainder of 0. And since I have a remainder of 0, that means that 2 is in fact a possible rational root. So if I was making you do this without a calculator, then you would have to continue and try the other 5 values. And when you try the other 5 values, you would find that none of the other ones gave you a remainder of 0. But to focus on the process and the theory behind it, you're allowed to use the calculator, and so therefore you are able to more quickly, with doing less synthetic divisions, find your rational roots. So the possible rational roots, like we said a minute ago, are right here. The rational root, in this case, is 2. There's only one rational root, and it's 2. Let's do another one. All right, so second example here, we're going to go ahead and talk about our P and our Q. So when I'm looking at this, my P is equal to 5. My Q is equal to 3. So now I have to think of all of the possible factors of both 5 and 3. So again, pretty simple here. So my possible rational zeros, so I'm going to say PRZ, possible rational zeros. That's going to be plus or minus P over Q. So I like to do these in order to try and keep it simple. So I'm going to be super explicit here. So each one of these has to go over each one of these. So 1 over 1, and then 1 over 3. Then I have to do the same thing with the next factor. So plus or minus 5 over 1, then plus or minus 5 over 3. So I am literally making every combination possible between these factors and the division. So I'm going to simplify here. So that's going to be plus or minus 1, plus or minus 1/3, plus or minus 5, plus or minus 5/3. And like I mentioned before, I like to write them in increasing order. Don't have to do it. I just like to do it. So plus or minus 1/3, plus or minus 1, plus or minus 5/3, plus or minus 5. All right, running out of room there. Okay, so now I'm going to graph. I'm going to get back out my graphing calculator. And what I'm doing is plugging this in. I already plugged it in to save some time, but I'm plugging this equation into my graphing calculator. I need to turn it on, and then I'm going to graph here. Hopefully it'll graph. Okay, there we go. So we can see here that there are 3 places where the graph goes through the x-axis. So there are 3 places where we have zeros. Now we have to see which of these are rational zeros. And again, the rational zeros have to be able to be displayed in this fraction form. So for this one, the 5 is pretty obvious. But these two, it's a little hard for me to tell. Is there a 1/3 in there? Is there a 5/3 in there? I need to figure out what's going on. So I'm going to go ahead and find my 0. So left bound, right bound, guess. So my 0 here is, I'm going to write it down, 0.23241. All right, now I'm going to do the next one. So second calc, so it's the second right here, second trace, 0. And now I'm going to find the next 0. So it's right here, left bound, right bound, guess. And this value is 1.43428. All right. And then the next one, so second trace, 0. Keep moving down my curve here. Need a left bound. Whoop, went right by it. Okay, left bound, right bound, guess. All right, sweet. That's 5. So 5 I know for sure is good. These other 2, I need to just make sure that they are not equivalent to these fractions. So 1/3 is 0.33333333, as you know. So nope, that's not this. And then 5/3 is 1.6666666. So neither one of these are rational roots. So I'm crossing both of these out, not a possibility. But 5 is on our graph as a root, and it's also in our possible rational roots. So now our job is to use synthetic division to prove that that is a rational root. So set up my synthetic division with 5. Then I'm going to put in 3, -20, 26, -5. All right, synthetic division, here we go. So bring down my 3. 5 times 3 is 15. -20 plus 15 is -5. 5 times -5 is -25. 26 minus 25 is 1. 5 times 1 is 5. And so I have a remainder of 0. So this is fabulous. Since it is a remainder of 0, that means 5 is a root. So our rational root, oops, for this problem is 5.